Introduce our last speaker of the day, Anatoly Golberg from Holon Institute of Technology, who will talk about homeomorphisms of finite metric and area distortion between Riemannian manifolds. Please.
Thank you very much. First of all, I would like to thank the organizers for the invitation to take a part in this great event and possibility to give a talk here. Let me only mention that some of topics raised in this focus program gave me a strong motivation to study these topics and to extend my further research in this direction. And I would like to start with the following well-known fact. The global conformality of a mapping, I mean conformality in a domain, provides a really strong rigidity even in the plane. In higher dimensions, its property becomes much stronger. It's, in view of the classical Liouville theorem, we have only restrictions of Mobius transformation, I mean restriction with respect to domain. So the quasiregular mappings are of greater interest, and let me cite this the well-known mathematician and outstanding mathematician and contributor of this topic, Seppa Riemann. It is the right extension of geometric parts of the theory of analytic function in the plane to Rn. So in this sense, quasi-regular mappings and around then can be treated as analytic function spaces. View of the topic of our program. And in higher dimension, there are three main approaches. I will touch everyone here: analytic, geometric, modular, and metric. Although in the main topic, which also relates to the topic of our workshop, will be metric presentation of such classes of mappings and or classes of mappings whose definition rely on metric approaches like finitely by Lipschitz mappings, quasi-symmetric mapping, Quasimobius, metrically quasiconformal mapping, and metric mappings of finite metric and area distortion. Although we will avoid to assume some analytic restriction, very interesting, very important properties like losing end condition, absolute continuity, and so on will be established. We need to involve also classes of mappings whose definition relate to purely geometric approach, modular approach, and we also discuss interplay between such classes of mappings in order to study the boundary correspondence problems related to weakly flat and strongly accessible boundaries between Riemannian manifolds. And once again, some of such examples can be treated as inner functions that are far advanced extensions of Blaschke products. And this talk is based on our joint works with Elena Afanasieva from Institute of Applied Mathematics and Mechanics, Ukraine. So, but usually quasi-conformality in the plane is connected to this homeomorphic solution of this well-known equation, which is called the Beltrami equation, and we say that F is a quasi-conformal domain G of the complex plane. If it has L-squared derivatives, the formal derivative by F of C does not vanish almost everywhere, and so on. But in higher dimensions, I mean Euclidean spaces, we cannot extend this approach, since even in the three-dimensional case, the system of Beltrami equations becomes over definite and nonlinear. So the analytic definition of quasiconformality, and here you can see also quasiregularity, only quasiconformality for homeomorphic and quasiregularity for continuous function, means that our mapping should belong to the Sobolev class W1 and locally, and this guy, which is called the outer dilatation, is uniformly conformed, uniformly bounded almost everywhere in the domain G. Usually, let me present the geometric presentation of this guy, and usually in higher dimension we use two more dilatation, so-called inner and linear dilatation. This is the analytic formulas for this expression. Here, small l is the minimal stretching. This is norm of the Jacobi matrix subnorm and Jacobi matrix, and this is the Jacobian, and this quantity are minimal and maximal stretching of the Jacobian of mapping f at point x. And from geometric point of view, under linear mapping f prime of x at point x, the image of unit ball Bn in Euclidean space in Rn is an ellipsoid. So the inner dilatation is the ratio between the volume of the ellipsoid to the inscribed ball. This guy, outer dilatation, is circumscribed volume of circumscribed ball to the volume of ellipsoid, and linear dilatation is the ratio between the biggest to the smallest semiaxis of the ellipsoid. In the plane, all these quantities coincide. In higher dimension, they are bounded in the terms of each other, so they are finite or infinite simultaneously. Okay, also if we go to quasi-regular mappings that are non-homeomorphic mapping in general, once again, in the plane by Stolov factorization theorem, any quasi-regular mappings is a composition of a quasi-conformal mapping and analytic functions. So one quasi-regular mappings are simply analytic functions, and we can see the same sentence that cited in the beginning of the talk. So quasi-regular mappings are necessary, in my opinion, and not only my opinion, extension of analyticity to higher dimension to Rn. Let me also mention that this class of mappings quasi-regular was introduced by Reshetnyak in 1966, and he called them mappings this bounded distortion, but nowadays this name is quasi-regularity. Okay, once again, quasi-regularity assumes that mapping belongs to the Sobolev class, and this outer dilatation is uniformly bounded by constant k almost everywhere in the domain D. This is analytic definition of quasi-regularity, and you can see this is the list of very important and interesting properties that can be derived from this definition. So any quasi-regular mapping has a continuous presentation, so it belongs only to the Sobolev class W1n. Moreover, f is Holder continuous with the exponent 1 over this constant k. F possesses losing n and n-1 properties, of course n-1 for non-constant, since any constant mapping is also quasi-regular. Let me recall briefly now that losing n and minus 1 properties mean that any set of zero measure has also zero measure. I mean, losing in the direct for the direct mapping and minus 1 for the inverse mapping. Also, from topological point of view, any quasi-regular mapping is open and discrete, once again from a constant mapping. Moreover, by the famous result by Bayarsky for the planar case, any quasi-regular mapping belongs to the Sobolev class W1P, that P is greater than, for the planar case, P greater than 2, and P depends on the dimension and this bound K. And this result, was extended to higher dimension by Gehring, but by absolutely different way, by using the so-called inverse Hölder inequalities. Probably one more important properties for higher dimensions. There is no analog, for example, of exponent. So any locally homeomorphic quasi-regular mapping of the whole Rn is quasi-conformal. So locally homeomorphic in the whole Rn means globally homeomorphic. And this result, it was conjectured by Mikhail Alexeyevich Lavrentiev of 1938, and in about 30 years, it was proved by Zorich. Two more words on extension of quasi-conformal, quasi-regular mappings, which is, this extension is very important from geometric and mechanical point of view. It is class of mappings of finite distortion. Here, the mapping should belong to the Sobolev class W1. This locally integrable Jacobian, and now this condition, the uniform boundedness, is relaxed by finiteness almost everywhere. And of course, various properties of such mapping can be obtained by appropriate assumptions on this distortion function, like integrability with some degree, or for mappings of bounded mean oscillation, and etc. And here let me refer to monograph by Ivanis Martin, Henkel Koskela, Gehring, Martin, Palka. And let me only provide the mechanical description of such classes of mappings, mappings, I mean mappings of finite distortion. So if we consider our domain as a solid body and F is deformation, continuity can be treated as no breaks, no cavities under such mappings. And invertibility says that it is possible to reconstruct the body and to come back to initial state, and losing n and minus 1. Property says no material can be created from nothing. Two more slides. Probably it is important to recall some general knowledge related to Sobolev classes. So if we would like to get a mapping of Sobolev class W1P, which is differentiable almost everywhere, we have to require that the exponent should be greater than n. The case is P is equal to n. The border case is still can not provide differentiability, since in this case there are mappings of this class which are not continuous at any point. The classical theorem is Stepanov's theorem, which gave sufficient condition for mapping to be differentiable. It is finite, is almost every of such guy. We will talk on this guy in more general setting throughout our talk and a little bit later. And if we require homeomorphity of our mapping, you can see that the exponent should be greater than n-1 for higher dimensions. In the plane, it is enough n is equal to 2. So mapping in the plane of Sobolev class W11 guarantees differentiability almost everywhere. And the last slide on regularity properties. Let me recall the condition which guarantee conditions which guarantee n and n-1 properties. So continuous mapping always satisfy losing n property with respect to n-dimensional Lebesgue measure only if p is greater than n. So even in the border case, it is not enough for continuous function, only for homeomorphism. Every homeomorphism of the Sobolev class W1 and possesses the losing n property. And also this result is important for us, the equivalence of non-vanishing Jacobians and n-1 property. It is due to Ponomarev and his paper of 1995. Okay, I mentioned at the beginning of talk there are three main approaches in higher dimension analytic. We have already this approach. We discussed analytic definitions. We also present modular approach, and as I said in the beginning, metric is the main our approach. So using this approach, we discuss Lipschitz and by Lipschitz mapping, I mean this constant L Lipschitz and L by Lipschitz mapping. This is a very important and for advanced extension of the previous mappings. This class is called finitely Lipschitz or finite by Lipschitz mapping. Also, homeomorphism of finite metric and finite areas distortion will be discussed in our talk, and also quasi-symmetric, Quasimobius mappings, and quasiconformal mappings from metric point of view. And of course, we will discuss between two Riemannian manifolds, and let me only say that by Riemannian manifold, we mean n-dimensional differentiable connected manifold, C infinity, equipped with Riemannian metric. Okay, this is the well-known definition of Lipschitz. So the existence of such constant L and the distance in the image is restricted from above by such product for any x of I provides Lipschitz mapping. If we would like to talk on by Lipschitz, we have to add the left-hand side of this inequality for some L greater than or equal to 1, and all points x and y from this manifold. And this mapping, of course, becomes isometric then L is equal to 1. And now this is definition of finite Lipschitz. Yes. So we require only that this quantity, you can see this, we have seen this quantity in the Stepanov's theorem. So this is quantity can be treated as maximal stretching this, and for finitely Lipschitz, it is not bounded. It is only finite for every point x, and finitely by Lipschitz, if we add in the left-hand side also the minimal stretching, and we require that this guy is positive for any point x from our domain. And let me illustrate this class of mappings by the following simple example. So let us consider homeomorphism in Euclidean space Rn, which is defined by the following formula. And in the unbounded cylinder, and cylinder here is cross product of the unit n-1 dimensional ball and unbounded interval 1 plus infinity. By direct calculation, we obtain that the maximal stretching is equal to xn to the power n minus p minus 1, and other such restriction. You can see that this guy is finite, but cannot be bounded from above. And the minimal stretching, I have only question. Do you see here these formulas in the last line?
Yes, everything is visible.
Thank you very much, because here are some things related to Zoom disturb me to see the last formula. Okay, so and the minimal stretching cannot be separated from zero. Okay, if we assume that these quantities are bounded from above and from below by 1 over k, they obtain almost the same. So by Lipschitz homeomorphism, and this homeomorphism, these bounded such quantities are equivalent. I mean, this definition equivalent, and this result is quantitative. So we have to consider to extend, essentially to extend Lipschitz, and by Lipschitz mapping, we have to consider only such inequality. For some of our results, we will require from the manifold in the image to be hyperconvex, or the injective metric space. We need this to apply Kinsbrown type theorem of extension of Lipschitz mappings, and these notions is due to Aranjan and Panishpagdi of 1956, who proved that hyperconvex space is a non-expective retract of any metric space in which it is isometrically embedded. And the classical examples of hyperconvex metric spaces are the real line and the Euclidean spaces with infinity distances. And next, our result says, if our mapping is finitely Lipschitz, satisfies for all point x this condition, then and of course, as I said, M prime is a hyperconvex space. Here k is any integer between 1 and n-1. So you can see the following condition. It is the losing condition with respect to k dimensional Hausdorff measure. So any set of zero measure also has zero measure in the image. It is very important, once again, for a change of variables formula. If we add in addition this, that L, small l is positive for every x from the open set, omega they obtain that our mapping is finitely by Lipschitz and possesses the losing n and n-1 properties. The class of quasi-symmetric mappings, you can see here the definition of eta quasi-symmetric mappings, was first appeared in the classical paper by Berling and Alfors of 1958. And this paper, the title of this paper is the boundary correspondence under quasiconformal mappings, although the name quasi-symmetry came 10 years later. And you can see here now that it is an extension, it is kind of extension of Lipschitz condition instead of 2-point condition, you see here 3-point condition. And moreover, if by Lipschitz mappings distort both the shape and the size of an object by bounded amount, this mapping gives us only an approximate shape. So it is a very reasonable, very important extension of Lipschitzness by Lipschitzness. And there is a weaker condition, which is called weak H quasi-symmetric condition. You can see here. And let me only mention that weakly quasi-symmetric mapping need not be eta quasi-symmetric in general. And also we discuss in our talk the class of omega Quasimobius. Now you can see instead of 3-point condition, you see here 4-point condition, and the guy in the left-hand side, also in this in the brackets, which why it is Quasimobius, since for Mobius transformation, this quantity remains the same, I mean, invariant. And also in our next results, we have to require from our domains to be C quasi-convex. C quasi-convexity means that the length of the curve that joined every pair of points does not exceed the product, this constant C, and the distance between 2 points. It is local quasi-convexity and quasi-convexity of a set. And our next result says, if we assume that 2 domains, Riemannian manifolds M prime are C quasi-convex, that weakly H quasi-symmetry, weak H quasi-symmetry, and eta quasi-symmetry are equivalent quantitative. Next, our result says that any L by Lipschitz homeomorphism is also weakly H quasi-symmetric homeomorphism with such constant H, which is equal to L square. This is definition of metric quasiconformal. And so you can see the same guy as in the definition of quasi-symmetry. And now if lim sub of this quantity is uniformly bounded for K, for all points of the metric space, it says that our mapping is metrically K quasi-conformal, and any K quasi, our next result states that any K quasi-conformal mapping is locally weakly H quasi-symmetric and vice versa, but only locally, since this simple example suggested by Pekar-Koskela shows that let us consider Riemann spheres without the North Pole, and by Mobius transformation, the lower half of this sphere can be mapped on the sphere without small cap centered at the North Pole. So in this case, since it is Mobius transformation, k is equal to 1, but the constant h can be bigger as possible. Our next result is that any quasi-Lipschitz homeomorphism is also k quasi-conformal mapping. And two more conditions. Let me only recall this. Holding Poincare inequality implies quasi-convexity. Very briefly, a Borel function is said to be upper gradient if the following inequality holds rho function. It is clear that rho is not unique, and for example, infinity can be treated also as upper gradient. And by the way, for Lipschitz mappings, rho can be replaced identically by the constant, I mean Lipschitz, but constant L, and X admits a weak 1p Poincare inequality is the following inequality holds for all poles. Please, let me pay your attention here that in the left-hand side, you see a smaller ball. And if lambda is equal to 1, this inequality is called 1p Poincare inequality. And holding this inequality allows us to reformulate the previous results. So the equivalence of weakly H quasi-symmetric and eta quasi-symmetric, and also the same any L by Lipschitz homeomorphism is locally H quasi-symmetric, and K quasi-conformality is equivalent to local H quasi-symmetry, and the last result also that any L by Lipschitz is also K quasi-conformal. Let me skip, I will define this guy, which is called the modulus of family of curves, even in wider form as a modulus of family of surfaces, but we obtained here, if we assume that our domain is of quasi-extremal distance, we obtained the same results. And let me skip these slides. And now we write to modular approach. Modular approach means that we will use this quantity to characterize our mappings. This is called the modulus of family of gamma. Gamma is the family of k-dimensional surfaces in Riemannian manifold M. Surface, of course, k-dimensional surface is a continuous image of domain in Rk in M. And the modulus is defined by the following formula. It is infimum over all function rho admissible for this family, the infimum of such integrals of rho to the power n. It is the dimension of our manifold. This is the volume element, and admissibility says that such surface integral should be strongly greater or equal to strongly separated from 0 for any surface from our family. So it assumes that it is greater than or equal to 1. Also, for some classes of our mappings, we have to extend this admissibility condition. It means that this row is called extensively admissible for the family of k-dimensional surfaces if it is admissible for almost every surface. Almost every means that it is admissible in this sense for family gamma, except for its subfamily whose modulus vanishes. And this quantity also is very important in geometric function theory since it remains invariant under conformal mappings, and any form of it can be treated as excavated modulus. You can see here at this way 1 over q. Q is given measurable function. So if the modulus is restricted from below by such integral, here the intersection, this epsilon, is the intersection of our domain with the geodesic ring centered at point x0. And if modulus is restricted from below by such integral at point x0, our homeomorphism is called lower q, lower because of this bound from below, and lower homeomorphism at point x0. So you can see this as extension of conformality properties. Since in the case of conformal mappings, this guy remains invariant. Once more, and we say that homeomorphism is low q homeomorphism. It is q homeomorphism at each point x0 from the closure of D. Let me only present this picture. So this is, we consider the spheres here, or more precisely, we consider the pieces of spheres, since we say that this intersection of these spheres, this domain D. And this is the definition of mappings of finite metric distortion. And you can see that this inequality for minimal and maximal stretching, like in finitely Lipschitz mappings, now should hold almost everywhere, and mapping F is assumed to be to possess the losing end property with respect to n-dimensional Hausdorff measure. And our next result says this is the connection between these classes of mappings and low homeomorphism. So if it is FMD homeomorphism with extra condition that losing end property should hold with respect to n-1 dimensional Hausdorff measure, then F is lower Q homeomorphism. This their Q is the outer dilatation of quasiconformality defined in the first slides of our talk. Let me only say that we defined in the case of Euclidean spaces, if we consider these quantities normal neighborhoods, these quantities, I mean generalized Jacobian in Riemannian manifold, and this quantity also on a Riemannian manifold agree these corresponding quantities in Euclidean spaces, and we obtain the following if we consider finitely by Lipschitz homeomorphism, that F is also lower Q homeomorphism with such Q. You remember the restriction on the losing end property with respect to n-1 dimensional measure. n minus one dimensional measure, we consider also the class of mappings of finite area distortion. There you can see a similar condition. So we have n property with respect to k dimensional surface. This restriction should have n property with respect to area. AK2 is this property in opposite direction. Since we consider also non-homeomorphic mapping, here the surface S is a lifting of surface in the image. So it is a composition of our mapping and surface S. And we say that our mapping of finite area distortion in dimension k if f of finite metric distortion and also satisfies a k condition, like in our previous theorem for the case that k is equal to n minus 1. And we say that f of finite area distortion if f is FAD k for every k between 1 and n minus 1 integer. Also, we need another definition of which involves modular approach. Now you can see the modulus of the family of curves. We join the sets A and B. Now you can see the modulus in the image is restricted from above by such also weighted modulus. Once again, it is extension of conformality, since for conformal mapping, this quantity remains the same. And this guy is called ring Q homeomorphism. You can see they consider only the family of curves, not k-dimensional surfaces, only families of curves. They join these sets, these compact sets C0 and C1, and this is in the image. And our next result says if we have a ring Q homeomorphism such that Q is locally integrable, then this guy, this maximal stretching is finite almost everywhere. And by the way, by Stepanov theorem, it means that any ring Q homeomorphism is differentiable almost everywhere in the domain. This is a kind of extension, so we consider both inequalities, such bounds, upper bounds for the modulus in the image and the pre-image. This due to the monograph by Martin Rezanov-Kubov. This class is called, this mapping is called hyper Q mappings. And if we consider here rings, we obtain hyper ring Q mappings or Q homeomorphism. And you can see once again the connection with our metric approach. If we consider hyper ring Q homeomorphism, this such a locally integrable function Q1 and Q2, we obtain that this chain for the minimal and maximal stretchings. And moreover, due to our previous results, f at n minus 1 both possess the losing n and n minus 1 property with respect to any k dimensional Hausdorff measure. Also, the following result shows that any homeomorphism of the Sobolev class W1 and this such condition, integrability condition on the outer dilatation, provides that f is ring Q homeomorphism, this such Q. And next theorem shows that if M prime is hyperconvex space and F is of finite area distortion for some k between 1 and n minus 1, that F both lower Q homeomorphism and ring Q star homeomorphism with such Q and Q star. Some very shortly on Quasimobius mappings. Let me recall that the definition of Quasimobius, by the way, this class was defined by Lucy Weissela after communication with Oli Martio. And you can see if the x4 is infinity and f of x4 is infinity, that any Quasimobius mapping becomes quasi-symmetric mapping. So this is the implication between quasi-symmetric mappings, Quasimobius mappings, and quasiconformal mappings. And our next result says that any omega Quasimobius mapping satisfying some small, very small restrictions, that if is mapping of finite area distortion, and moreover, this quantity and this maximum stretching is locally integrable in degree n. Now, in the last part of my talk, first of all, I would like to present some interesting examples, and some of them can be treated as inner functions. For example, you can see the following, and we discuss very shortly some boundary corresponding results applying for such mappings. This mapping carries out the punctured unit ball onto the spherical ring. All these examples are given in Euclidean spaces, this radii 1 and 2. And you can see this mapping of finite metric distortion, since all this quantity satisfy the following quantity satisfies the following condition, and since it is a diffeomorphism, it possesses losing end property. This is an automorphism of the punctured ball also, and you see it is also mapping of finite metric distortion, and this mapping, in contrast to previous one, has a removable singularity at the origin. Two next examples you can see here, it's also it is classical quasiconformal mapping of such a form. It is also mapping of finite metric distortion of the punctured ball, and also it has a removable singularity at the origin. And this mapping is a rotation. If we restrict ourselves to three-dimensional case, it is a rotation around the axis of axis x3, this quick rotation, since as x1, x2 approach 0, theta increases very quickly, and this mapping also preserves the volume. And moreover, this mapping is by Lipschitz with such constant, and also it is metric of finite mapping of finite metric distortion. Of course, for boundary corresponding problems, we have to restrict to give some restrictions on the boundary, like smooth boundaries, and we will discuss in our theorems weak flatness. It goes back to property P1 by Weissela, which means that if we consider two subsets of domain D such that their closure has non-empty intersection, that the modulus of the families of coordinate the sets E and F is equal to infinity. And this example of non-weakly flat at x0. So it is, if we restrict ourselves to two-dimensional case, then the boundary consists of this closed curve, and this interval segment originated from x naught. Why this mapping fails to be weakly flat? Since due to the properties of modulus, it should be restricted from above by a constant. And you can see in this definition, the modulus can be greater than any constant, given constant p. And a wider condition is strongly accessible. Let me illustrate by example what is boundary, what is point which fails to be strongly accessible. If we consider two combs, the tips in opposite direction, such that the distance here between tips goes to 0, and here compact set E located here, and for any compact set F which intersects both the boundaries of neighborhoods U and V, so we can connect these sets only by rectifiable curves. I almost finished the talk, and so at the family of such family of rectifiable curves, and rectifiable curves is equal to 0. So in this case, there is no constant delta. And our next result shows that for appropriate condition on homeomorphism of finite metric distortion like this, the inverse mapping has continuous extension. It can be discussed by our mapping, so we can show that sometimes our conditions are not only sufficient, also necessary. Next result says that such condition, asymptotic condition on integral, also provides to extension for weakly flat homeomorphically, and strongly, in the case of strongly accessible, only continuous extension. And one more last result also says that such asymptotic behavior of mappings of finite metric distortion can guarantees homeomorphic for this case and continuous extension for this case. Thank you very much for your attention.
Thank you, Anatoly. Let's thank Anatoly for a wonderful talk. Questions, comments, suggestions?
I have something, but this is very naive. I mean, Anatoly, in early part of your talk, you emphasized a lot on bi-Lipschitz function. And I mean, since I don't know the subject, I don't know why you emphasize on regularity from below. I mean, is that essential for your result?
For finite bi-Lipschitz, because okay, just a moment.
Because we usually control it from above, but you also want it.
No, it is for bi-Lipschitz because just a moment, Gerard. Let me show. Now let me show the following. Apologize. Do we see it? Do we see my presentation?
I see the last slide.
Yes. Just a moment. It was much easier to come here. Why? Okay. You can see this example. Example here. This example, and for this case, this guy cannot be separated from 0.
True.
So it is very important. It's very important for us, since in the case of a regular bi-Lipschitzness or abi-Lipschitzness, it is restricted. It is restricted from below by 1 over L. And in our case, it is essential, very essential extension. So So any by Lipschitz mapping is also quasi-conformal, but we have examples that such mappings finitely by Lipschitz mappings is found to be quasi-conformal. I hope I answered your question.
Yeah. I missed the example 1 over xn. Yeah, it is true. Thank you. Thank you, Anatoly.
More questions, comments? If not, let's thank Anatoly again.